All right, hello. Let's look at another book this week. I'd like to look at this guy here. This is by Anthony Sudbury, Quantum Mechanics and the Particles of Nature, an outline for mathematicians. So you may have heard us talk about this on the old podcast when we were trying to read through another book. I'll probably talk about that later, called um, Quantum Paradoxes. I'll probably talk about that later. But sort of in the middle, since we'd just taken a break, we wanted to look at something a little bit easier and a little bit on a different scale than that book. So we were looking at one of the chapters in Quantum Mechanics and the Particles of Nature. Shortly after we did that, I'd worked through the book itself. Let's raise this up, get a full look at that guy. So I worked through the problems. They're fairly interesting. It's a reasonably nice book. Do I have it? Yes. So this was, again, after 2013 that I read through it. I know I read parts of it. I'm not sure if I read the entire thing when I was an undergraduate, but I did pick it up back then when I saw it, whether it was at the tattered cover or at the bookstore of the school, I don't know. The school bookstore on the area campus, was actually the best school bookstore I've ever been to. It had all sorts of fun things sitting in there. It would have Springer books and stuff like that, and that's sort of where I got this guy from. Let's see, or probably where I got this guy from. There was a bookstore called the Tattered Cover that also had very good things. So at that point, I didn't order things in from Amazon because there was no such thing as an Amazon. There's me trying to write a poem about a neutrino. I don't know why I would want to write a poem about a neutrino, but I did. Now, this is a little bit different from your normal quantum mechanics book, because it's a kind of quantum mechanics book for mathematicians in a way, is sort of what I felt. Now, I have another book. Maybe I'll get to that in 2 or 3 years. It's called Quantum Mechanics for Mathematicians, which is interesting. I actually had a functional analysis teacher, who said at the bar one night that, oh yeah, he looked into quantum mechanics and it was easy. And it is, if all you're doing is you're saying, okay, well, quantum mechanics is its Hilbert space and so on and so forth. It's a very simple application of functional analysis. So, in any event, this is the actual book. So you see, this is the first chapter just talks about particles and forces, and goes through the different particles that we know of, or at least the simpler ones, sort of at a level that's similar to, say, a modern physics summary, and maybe a little stronger than that. And it talks about forces. So I think I do not know. There are two choices for this. I'll take off my glasses and just look through here. This is where I first saw, I think, there's a rate equation. Let's see. There's a nice list of the leptons. It's at 17. Here's a list of gravitation, electromagnetism. There we go. The fundamental forces, which sort of give you the strength and the range. So when you talk about the range, you're coming over to this equation here for the potential. So this is your potential energy for a general force, and these are the 4 forces. All right, and there's electroweak unification eventually at some point. When people talk about things, let's say like a 5th force of nature, I'm always wondering, well, what does that mean in terms of this equation? And that's partially because I got introduced to this at a fairly young age, only about 25 or so. So let's go back and see these things. So this is where I saw that analysis of force. It's a really interesting way to go about it. So that tells us about the particles, the sort of things that are affected by quantum mechanics normally. I mean, obviously, we've all seen now that we can get much, much larger things to be affected by quantum mechanics. We can get interference effects in buckyballs and things like that. Then he goes through quantum statics. We've got some examples and a note on probability. Probability is important, and it's even more important in quantum mechanics because you calculate it strangely. And in fact, that gives you two different kinds of observables, right? You can observe a quantum state, or you can observe something from an ensemble. So those are two different ideas, right? And sometimes you get results from one, and sometimes you get them from another one. And here we're going through a lot of things. Basically, you've got a bunch of math, and you're talking about observables and what they sort of mean, right? So that's a very interesting thing. And combined systems, that's your entangled particles. So this is just for things not moving around, and there's some talk about identical particles. It's been a while since I've looked at this. I'm not sure. It probably doesn't go into this is what, page 70? Probably does not go into it does. It goes into the different kinds of particles for quantum statistics. Okay, so that's interesting. It's a little early for that in normal things, but of course this is not a normal book. That's why I'm reviewing it in part. It has an interesting take on things, and it's, again, more mathematical. Then we go to quantum dynamics. Not really a strange idea. All of a sudden you want to put in the time operator. You want to start moving the wave function around in time, right? Because that's what happens. That's what we care about. So that shows up, and you get perturbation theories and a brief description of Feynman's quantum mechanics. Then you get some quantum systems, different sort of things, addition of angular momentum, different systems, two-particle systems, hydrogen atoms, harmonic oscillators, annihilation and creation operators, which are really important, and in some books are the only thing you use. So that's more advanced books. So that's important. I mean, it's a different way of looking at quantum mechanics. Now, quantum metaphysics is the thing that we looked at in the episode, right? This was basically looking at ways people think about quantum mechanics. And now talk about statistics and stuff, but the important thing is you've got this quantum theory of measurement. That's where Schrodinger's cat shows up. But it's also where most of the problems in interpreting quantum mechanics are. So those first two chapters are basically talking about what happens with the wave function most of the time. And maybe it talks a little bit about, okay, well, when we make a measurement, then we calculate the probabilities and stuff like that. But you have to get some idea about what's actually going on with the measurement and what that means. And that's a little bit difficult. That's a weird thing for people. And I think the highlight of this chapter is going through all of the different ways you can talk about quantum mechanics, the alternative formulations, and the interpretations of quantum mechanics, which in specific we talked about in the episode. It goes through quantum numbers, and now you're getting back into your particles, getting back into particle physics, and you're talking about your isospin, which is a fairly strange beastie. So now you're getting into things that are more complicated than you'd normally learn in a junior level class again. I guess it depends on where you are, but probably more complicated than what you're going to learn as an undergraduate. And then quantum fields. Got your Klein-Gordon equation and your Dirac equation. So early kinds of quantum field theory, getting into quantum electrodynamics and gauge theories, quantum chromodynamics, and then more symmetries and stuff, which are the things that the real physicists care about. So that's what they do with the standard model. And is there another chapter? No, that's it. So we start with particles, we end with particles, right? We start with what the particles are and end with, in quantum fields, the particles of nature, particles and forces. And in between, there's a nice journey through the way all of these things work. All right. So, I mean, it's a really interesting book. Once again, I really like this. It's a little more mathematical. Let's see if we can find some of the problems. Now, I shouldn't say that too much. When I was a student, the professors always complained that I might not remember the way they might not remember their notation. Sudbury has very mathy notation. You can see that sometimes with some of the things we've just been flipping past. And there's a proof for 3.11. Like I said, this is from a mathematician. Quantum systems. Okay, there are some questions. Let me see. Do these look much different? No, to be honest, looking at some of these things, they don't look much different to me than the problems I worked with in Sudbury a couple of years ago. So, I mean, I didn't do anything with this Galilean group, but, emphasis and focus, different people have different ideas about what's so important. So maybe I was wrong. Maybe these aren't so different, but they do have a feel when you're working them that they're a little bit different from what you'd look at in a standard quantum mechanics book. So there it is, Quantum Mechanics and the Particles of Nature by Anthony Sudbury. Very nice book. It's one of the ones that we've talked about on the podcast. And it's absolutely positively not in print anymore. I will put an Amazon link to wherever they are. When was this? 1983? 1985. Okay. So in York, England, not Pennsylvania. So, thank you very much for listening, and I will choose another book to talk about next week.